Biagio, Lucini. There we go.
Okay. Can you? Non vedo niente. Okay, next. Okay, so let me thank the organizers for the invitation. What I will tell you about today is a method that we have developed recently that has various applications and in particular can be applied to the same problem. Okay. I also realized that I'm the first speaker this morning to talk about this conference, to talk about the same problem. So let me start by giving you my personal perspective on it. So what's the same problem? Well, we have a path integral or a partition function of this type. Ideally, the Boltzmann measure, which is identified by the integral over the fields times the exponential minus beta the action for the Hamiltonian, ideally this Boltzmann measure will be positive definite, and we can apply Monte Carlo importance sampling methods. But in fact, there are noticeable physics examples, including QCD at not zero temperature, but not limited to it. Another application we have heard yesterday from Lawrence are strongly correlated electron systems. Because of this, we are forced to consider actions that are complex. Yeah? And if we insist in solving this problem with numerical methods, then all the technology related to Markov chain Monte Carlo importance sampling falls apart, and we face with a numerical difficulty. So the same problem is the numerical difficulty that arises when we insist to solve a complex action system via importance sampling Monte Carlo methods. Okay. First of all, can we solve all the same problems at once? Well, the answer has been worked out by Troyer and Bisse some 10 years ago, and if we are able to do that, we will prove that problems that can be solved in polynomial times are equivalent to problems that can be solved in non-polynomial times. And as a bonus, you win one of the Clay prizes. Okay? So probably not. Probably not. So what we are looking for is for problem-specific solutions. And we hope that the problems we are interested in fall in that class. The other remark that I have in this slide is that the same problem may arise just because we are choosing the wrong variables among inverted commas. In fact, there are many systems, a few of them with very high physical relevance, that can be solved just by dualization. And in dual system, the same problem does not arise. Yes, but let's be stubborn, let's go back to that, and let's insist. So what have we done so far? Well, you can just take methods that we use in standard importance sampling and have modifications of them that hopefully will adapt to the problem. I just made a non-comprehensive list, which includes reweighting, imaginary chemical potential, cumulative expansion, and Taylor expansion. Okay? Most of them will be discussed at this conference. But what seems to emerge is that we need radical new approaches. And in recent years, we have tried complex Langevin and Timball methods, plus many more. And to this list, I want to add the density of states. Now, for those of you who have been around for a while, this may seem as a déjà vu. The density of states has been tried in the past and has failed. But this was a density of states that was based on importance sampling. What I'm going to propose here is a novel approach to the density of states that is based on a Markovian sampling inspired by a famous paper by Wong and Landau at the beginning of this millennium. So the material that I've used for preparing this talk is taken from this published work in collaboration with Kurt Lackfeldt, Antonio Rago, Roberto Pellegrini, and Lorenzo Bongiovanni. I will also talk about a recent work of Nicolas Garon and Kurt Lackfeldt. And I want to thank all of them for sending me material, in particular Nicolas, sent me all his latest unpublished results. This is a field that is becoming very active. So there is unpublished material that you might be able to find online. In particular, I want to point your attention to the plenary talk given by Kurt at the Lattice conference, and to the talks given by myself, by Nicola and Roberto, always at the Lattice conference. Philippe will add something more immediately after me. And there is a related method pushed by the Graz group that is a modification in the calculation of the density of states following ideas that we have proposed. There is this recent work in particular that is very, very interesting. Yeah. So this is an outline of my talk. I will start by seeing how the method performs when you don't get a same problem. It's a new method. We better make sure that it works before we do something that is fancier. So we'll start by saying how we formulate the method, and I will discuss three applications. The first two are quite classic. The one, lattice gauge theory and QCD Potts model, in particular what we can see about the phase transition in these systems. And then I will move to a recent application, which is the energy momentum tensor, for which we have only preliminary but very nice results. In the second part of the talk, I will finally move to the complex action systems. And again, I will see what changes in the method, and we'll discuss three applications. And finally, I will conclude, and I will list what, in my opinion, are the open problems. But let's start with the formulation of the method. So let us rewrite our Partee integral. I will use the quantum field theory language, but the method is equally good for statistical system. I'm considering here a system with an action that is continuous. And what I'm doing is that I can introduce the density of states in the form of a delta function. If I integrate this delta function over the energy, I obtain 1. Inserting the identity resolved in this form, I can rewrite the partition function in this way, where the quantity rho here is the density of states. Now, if I know exactly the density of states, well, I've solved my problem because I can compute free energies, and from free energy all the thermodynamics. At the same time, I can compute observable just by a numerical integration over the density of states. So far, it's just a reformulation. What we need to make sure is that actually it's a well-defined reformulation, and we are not trading an impossible problem with another impossible problem. Okay. This is in one slide where I try to summarize what we do to compute the density of state. First of all, let me call it rho tilde, because at this stage I will give you a recipe for computing a function. I will still need to prove that that's the correct density of states and which limit is the correct density of states. Now, whichever function of the density, in particular the log, can be linearized in a sufficiently small interval. So what we do is we divide the whole energy interval in n subintervals, so some amplitude delta E, which is small, and then we use the linearized form. In each interval, I can define a double angle expectation value, which depends on the linear coefficient an. And in particular, I can see when this double expectation value is equal to 0, which amount, if I choose as an observable the difference of the energy with the mean value of the interval, the solution of this stochastic equation will give me the coefficient I'm looking for. Now, we know how to solve an equation numerically. This is the Newton-Raphson method. If the equation is stochastic, we can use the Robinson-Monroe method, which was introduced more than 50 years ago in a paper that on Google has more than 4,000 citations. So what Robinson-Monroe say? Well, you can use this iteration here, in which if you start from a trial value of your coefficient, you correct it for something that looks like the function you're after over the derivative of that function. And that will be plain Newton-Raphson. But in front you put a coefficient over an over-relaxation term, which decreases as you go on in your calculation. Okay. So essentially this is a damping term of the Newton-Raphson recursion relation. This alpha can be worked out explicitly to minimize the variance, and this delta squared can be worked out in the same approximation, so the formula simplified but I wanted to put it straight just to understand where it comes from. And the derivation and the applications is given in the second paper cited here, while the first one gives the original idea. So I can take the infinite limit of this sequence, and I can find the n. But the second and probably most important result of, I just oversaved, the second and probably most important result of the Robinson-Monroe theorem is the red line that when it comes back
I don't know how did you manage that.
I can try again if you wish.
I would say it's enough. Non so che fare, spento questo, bisogna aspettare che ributtano.
Ci ho pensato che fa così.
Non che io sappia.
This never would have happened if you would have talked about complex language.
Good. I actually hope you're right. We will see later.
Non deve essere andato, non posso spegnere quello con questo, impossibile, va solo di là.
Come on.
Deve essere saltato da
So light was good for the progress.
Yeah.
Okay, any questions so far?
What about that plot? You can continue to talk about
Che lampadina, no?
Forse no. Ok, no, it's switching on. A bit of suspense.
Okay. Good. Okay, let me restart. So this is the Robinson-Monroe recursion relation. And what we can do is actually to truncate the relation, and then what we know is that the distribution at fixed m that we found is Gaussian and fluctuates around the value that is the solution of the equation. So you can repeat your experiment and you can compute that value, and you can use the replica, the series to do error analysis and to estimate how far you are from what is your error that you have on the observables. The last part is easy. The coefficient Cn can be reconstructed by imposing that this log rho tilde is continuous at the edges of the interval. Yeah. Now, if you restrict in this way your expectations, you might disconnect your field configuration. So how do you avoid that?
So that's just basically a linear spline that you're building?
Which one? This one?
Well, just once you determine A and C, it's a linear.
I want to determine this function here as a linear piecewise function in each interval. Okay.
Right, demanding linear, just piecewise continuity.
I demand linearity in the interval and piecewise continuity.
Yeah, can you get the first derivative also? Because
That's-
that would turn it into a cubic spline.
The first, well, you mean another derivative because this is the first derivative. The an is the first derivative of the function. Okay.
No, but usually with the cubic spline, you can get continuity of the function and the first derivative.
It's not a spline.
It's not a spline. It's not a spline. You might want to do a spline, but this is simply the most direct method.
Okay.
Okay. So what you do is you can replicate your sequence, but the second sequence you can translate by alpha interval, And then when the energy is compatible with being both in the upper and in the lower series, you might propose a swap of the configuration with a metropolis step. In this way, by hopping up and down, your configuration can travel all the energy space, and this way you can recover ergodicity. Now, in this paper, we spent quite some time, and we went quite at some length to prove the properties of this function. So the first thing is that in the limit for delta E going to 0, the Rotilda V converges to the density of state. And that's the first rigorous result. And since it's a mathematical theorem, I need to add this caveat, which is except for a set of points at null measure, which you don't, in principle, you can disregard. Now, this first derivative that George was pointing out, in the limit delta E going to 0, has a physical meaning. Log of rho is the entropy of the system, so the derivative of the entropy with respect to the energy is the inverse temperature. So in this way, you are computing the microcanonical inverse temperature. So this tells you that what you are actually doing in this method is you are trying a microcanonical sampling. What happens for observables if I use Rotilda at fixed delta E? Well, if I compute the average in this Rotilda ensemble, what I will find that this will convert to the observable that I want in the starting ensemble plus correction of order delta E squared. And last but not least, this function, well, the method enjoys exponential error reduction, which means that the error, the relative error of my function is constant. So it does not depend on how big or how small this function is. Now, what else do we get from the first indications? And why do we want to use this method? So, first of all, the method is more efficient at metastable points, and it looks like it has a polynomial cost rather than exponential. Then it can allow us to compute partition functions directly. And finally, the very reason why I'm giving this talk is it may enable us to solve the same problem. All this is supported by available numerical evidence, and the rest of the talk will be spent in discussing this available evidence. In addition, other indications are, first of all, that the convergence is precocious in delta E. Otherwise, it will be completely useless if you need to go to very, very small energy. You will get a high computational time because of that. Then, if you really want to see what happens at final delta E, if you want to be precise at final delta E without relying on extrapolations, you can correct this delta E squared via exact methods, for instance, a multi-canonical algorithm. And finally, you can extend the method also to observables that do not depend on the energy.
So you will reduce it for each observable.
Sorry, same thing.
You will redo the algorithm for each observable you want.
Well, you can redo the algorithm for each observable, but there is also a direct way that we are proposing in our paper, but at the moment is untested. There is a formula there that is untested. Okay? Well, I mean, the formula is fine, the efficiency is untested. Okay, let's start from the pure gauge theory, and you will see the density of state of an SU2 and SU3 on 10 to the 4 lattices. Let me draw your attention on the scale. So this is the log base 10 of the density of state. And this number here, which refers to the calculation in SU3, is minus 250,000. So these are the order of magnitude at which you are able to compute your density of states, without appreciable degradation of the quality on this scale. Then you may want to compare the reconstructed plaquette with a plaquette that you find with an important sampling algorithm, and this is what you get. So this is the level of the agreement, which is, I don't have a zoom, but is within errors. And finally, this is the similar plot for SU3. So this is the first convincing evidence of exponential error reduction. Now let's see what we do with that. And let me go to the first application, which is U1 lattice gauge theories. Now warning, I'm not presenting many formulae concerning systems because I'm more interested in the physics application rather than the peculiarity of the system. The only thing that I want to say about human lattice gauge theory is that it is somewhat a system that has been debated for a while. We know that there is, in modern language, a quantum phase transition, but it has been not clear, since it was very weak, for a long time it has been not clear whether it was first or second order. Finally, with the use of supercomputers at the beginning, some 10 years ago, the issue seems to have been settled for first order. So this is the determination of the A in the critical region. And as you can see, as a function of the lattice size, so the black at the top is an 8 to the 4, and then as you go down, you arrive to a 20 to the 4. As a function of the lattice size, the density seems to converge. This is for a specific delta E. Now let me take an observable, which are chosen to be the specific heat of this system, and these are the corrections that you get in delta E squared. All our points for different lattice sizes fit exactly the quadratic ansatz, and you can extrapolate to the 0 delta E limit, which is exact. Well, the cost of the algorithm seems to be quadratic in V because you don't feel the phase transition, and I will come back to that in my next slide. But first I want to show you, since it is a new method and you might not trust it, how good or how bad we are doing with respect to the multi-canonical. Well, the black points, black dots are the LLR, and the red squares are the multi-canonical, and they fall on top of each other in this curve for a 12 to the 4 lattice. And here you will see the difference. Just note the scale, which is of the order. Well, this is 10 to the minus 3 here. Okay? The errors are of this size due to the fact that you are very close to a phase transition, where it makes sense to do the comparison, or where, if you wish, you may have more doubt about the new proposal. And as you can see, is perfectly aligned with the results that you get for the multi-canonical. The remark that I want to make is that we don't need supercomputers, even when you rescale for the fact that the simulation of Arnold et al. I was referring to earlier has been done more than 10 years ago. And the reason is the scaling of the time that is quadratic. Again, I will cover that later in my next application rather than exponential. So just as a showcase of the method, here I put a plot on the 20 to the 4 lattice, and nobody else in the literature was able to produce the 20 to the 4 lattice for this system. So this really is a change in the method that actually determine a step change in the things that you can do. And this was done in a couple of weeks on not even state-of-the-art cluster. Let me go to a template method. So since we know that we have indications that the method works very well at first order phase transition, let me move to the template method to investigate first order phase transition, which is the Potts method. Let us start with a scan of the reconstructed energy of the model, expectation of the energy, with respect to beta, the inverse temperature. We do this for L equals 16 and in 3 dimensions. And here you can see a clear jump in the expectation value as you increase the number of the states. The blue curve is Q equal 10, for which the transition is already very strong first order, and you go down to the Q equal 2, which is the black curve up here. The vertical lines are results from independent numerical simulations, which we have taken from this paper by Bazalov, Berg, and UB. Now we go for a precision study, and for this we use the Q equal 20 in 2 dimensions. What I have here on the right axis are the intervals that are chosen, that you can see in various shades. So there are various intervals on this axis. This is the probability distribution reconstructed at criticality, then you take an action that corresponds to one of the nastiest configuration when you get interfaces, and you want to see how these actions actually, how this configuration, when you start from this action, particular action, actually travels in configuration in energy space. And what you can see here is reminiscent of a random walk, but we can go into more details. If it is a random walk, then the diffusion time will follow this law with the diffusion coefficient, and the diffusion coefficient is, from the data, is nicely fit by this ansatz with this value. We have also checked that it actually does not depend on which interval you start from. Also, let me remark that this curve I put here for reference, but the method does not know about beta. It's a microcanonical method. You only know about the energy at which you restrict it. Now, if I define the beta critical at finite size as the beta at which the two peaks, the ordered and disordered peak, are equal height, then first of all I can do a finite size scaling of the beta critical, and then from the valley here I can compute the interface tension. So this is how the finite size scaling of the beta critical goes. There is still some work to do because the errors are obviously overestimated in this plot. This is a very, very fresh result. But first of all, what I want to remark is that you obey the first order ansatz with very good accuracy. The error is of the order of 1 part per million, and is perfectly compatible with the exact value that you have for the Potts model. And now the interface. Well, to retake what I'm saying, if I define the peak to be equal height and I normalize the height to be 1, the probability to be 1 at maximum, then the order-disorder interface, so the energy associated to the fact that two different phases are touching, can be extracted by considering this quantity appears, so the logarithm of the probability in the valley rescaled by 1 over L. If you subtract the entropy related to the fact that the interface can form everywhere, then you have this ansatz, and this is the value that you get. There is a result in the literature which is due to Borgs and Janke, and this is the result that I report here. This is a strong coupling result that works surprisingly well, but is not exact. So I can compare our first preliminary result in the Borgs and Janke, and there is a discrepancy at 3 sigma that we need to sort out, but certainly can be due to both. Okay, now I go to my final application at zero density, at zero chemical potential for real action, and this is the energy momentum tensor. We have already had quite a few interesting contributions on the energy momentum tensor. It's a very important quantity for thermodynamics because it allows you to extract the equation of states, and it's a very important quantity also for conformal gauge theories because it tells you about the conformality scale invariance properties of your theory. But on the lattice, you break translational invariance, so you need to be careful and categorize the reducible representation of your energy momentum tensor with your residual invariance. You get a non-trivial renormalization, which is non-perturbative, and you have to compute the coefficients. One way to compute the coefficients has been given by Giusti and Pepe in this paper. And in particular, I'm focusing on the overall coefficient z of t because it can be expressed as a free energy. So if my method is good at computing free energy, you must be good at getting this coefficient. The method is based on a shift of the boundary conditions. So when you travel in one direction, you do not go back to the same point, but you are shifted by some vector, which is this psi here. These are the density of states for two different shifts, which goes in this way, again, over several order of magnitude. What I want to remark is that they are very similar, but there is a difference that you can appreciate on this insect. So if you want to compute then the delta F, which is related to this renormalization coefficient at two different shifts, you insert a beta and you do the calculation of your density of states, and this is the value that you get. For this example up here, the fact that you get a non-zero value is due to the fact that you can appreciate the shift of the curves that you obtain after integration, after convolution with the Boltzmann weight. Okay, so this is work in progress, so I don't dwell too much on it, except for one fact. There is one technical modification that we have done while doing this work, and we have replaced the projector into the energy interval with a smooth function, a Gaussian that essentially localizes your system in the same energy interval. One can do all the machinery, and one discovered that all the Robinson-Monroe procedure goes through, pretty much unchanged. The advantage that you have is that you can reinterpret this as a modification of your action, and if you have an action you can express a potential, then you can do a global HMC, which can be actually the first step toward the inclusion of dynamical fermions. Now, in the last part of the talk, let's move finally to the complex action systems. I have to confess that that was one of the strongest motivations to develop this density of the state methods. So we need to see how it performs. What has changes? So we go back to our partition function whose action as an imaginary part. Now we have two parameters, two couplings. One is beta, and the other one is the chemical potential mu. We can define a density of state with respect to the conserved charge that coupled with Q. So we introduce a delta over Q this time, and what would be zero density Boltzmann measure is reabsorbed into the definition of the density of states. Okay? So we work that out with a standard Monte Carlo, and as a function of that, we work out this function rho of Q. And now you can see that your partition function is a Fourier transform of this density of state. So that's the physical interpretation of the density of state itself. Now this is an oscillating factor. There will be cancellations over several orders of magnitudes. You really need to be very good at computing this rho of Q. And now the question is, how good we are? So why do we have hope? Well, one can consider the expectation of this factor here, the Fourier weight, which is the phase. I mean, what makes your system complex? If you neglect it, you get what is called the phase coefficient system, and then this expectation can be rewritten as the ratio of two partition functions, which goes like the exponential of some free energy density times the V. And that's the reason why all reweighting methods you can imagine generally fail. It's because of this exponential here. But this is an overlap problem. And I've already shown in the case of first order phase transitions that we can solve overlap problems by seeing that we can travel into the region with depressed probability. Now, is it also true that the same solution actually can allow us to get away with the same problem? Well, by itself, if you repeat the procedure and you try to do the integral with the piecewise approximation, you do not get enough accuracy, and you immediately understand why. At the edges of the interval, you have singularities, and these singularities are going to give you a contribution to your integral. So you need to smooth these singularities. So you need to somewhat compress all the information you have. And the way to compress is to fit the density of states. And this is what we proposed with Kurt not long ago. And essentially what you do is you fit with a polynomial ansatz. The polynomial can have a pretty high degree to approximate your density of states because you have information about that counts from 1,000 points or more. So fitting a degree 40 polynomial is not an issue. You still have plenty of degrees of freedom to strongly constrain your system. And there is a new method that has been very, very hot from the press that has been proposed by Nicola and Kurt, which we will talk about later on. So let me start first with what we have done and what is published. And let me start with the first model that we studied, which is the Zipf model. For once, let me write the partition function of this system. So this is the physical interpretation is that you can obtain it from QCD if you consider large fermion masses and a finite temperature and non-zero chemical potential. So the system ends up in a three-dimensional spin system, which essentially couples the remnant of the Polyakov loops. And you can add a chemical potential for them, which makes your partition function complex. Which makes your action complex, but the partition function is still real. Why we choose this model is because we have comparisons we could make with the literature. Let's take an observable that is actually very sensitive to cancellations. Now, one possibility is the phase twist, which is the difference of the spin pointing in one of the complex direction and the other, normalized by some factors. Again, this is the ratio of a partition function. This is the original partition function, and its derivative at the top. So we may study as expectation functions over the phase quencher system how this will go. And you have them over here. Well, you see that it goes over 20, both of them go over 20 order of magnitudes. So you do have a same problem. But then, when you put them together, you get a number that is order 10 to the minus 2 or 10 to the minus 1. And you agree with some control on the fit that you do have with the dual, with the algorithm that is based on dualization of the system. Okay. So this is a first test that we can actually do what we are set for. The second test comes from the Bose gas. Here we are compared with the results that Gert kindly gave us based on a mean field calculation that he did. And here you can see our data for the Bose gas at different mu for the delta F that I've plotted up here as a function of the chemical potential, and it goes through the lines of the mean field. It was already proved by Gert that the mean field is actually a good description of the system. Now, if you worry where the same problem is, well, you reinsert back. There is a missing log here, obviously. Okay? I forgot to put the log at the numerator of this expectation value up here. So we'll see that if you reinsert all the volume, you will see that this is order e to the minus 120 for a chemical potential that is here. And finally, I'm going to discuss work that is not mine, but is from Kurt and Nicolas. And there is a preprint on the archive. So what they have done is they have studied the evidence system at the choice, for instance, at this choice of the parameters, and then compare what happens if you take the system, a scan in the chemical potential. So they provided results obtained with some conventional sampling based on reweighting, which works very well for this system, and they provided a result for the LLR. I invite you to read the papers to read about the good features of this model. First of all, you get a particle-all duality, which essentially gets rid of the same problem at small mu, as you would expect, but also at mu. And then there is an half-filling point in the middle where you still do not expect to have the same problem. I mean, somewhat surprising, but in the end, there are analogies in the literature that you can make, and you see that you do not have the same problem. This is in this work, and what I've not reported is essentially that if you zoom in this area, you will see that you get strong cancellation, a result that is very close to zero on the black dots, which is the conventional sampling, while the LLR can resolve the signal over there. And finally, it's somewhat unsatisfactory, the fact that you have to have a polynomial ansatz to express your density of states. So what we are looking for is a method from first principle. So Kurt and Nicolas have tried expanding the distribution that you get in cumulants of the distribution. The cumulants are essentially the momenta of the distribution, which in quantum field theory you can think of them as the connected functions. So if you compute the momenta, what you will see is that if you go in the variance, for instance, is not enough to describe the data, but as soon as you go to the next leading order, in this scale, you get perfect agreement. And now I do have a couple of zooms courtesy of Nicolas. So see that the error that you make truncating the expansion is, first of all, can be resolved, and then it's very high if you just use the first cumulant, which is the variance of the distribution, which would be exact in the Gaussian approximation. But then, as soon as you add momenta, you basically have perfect agreement. And this is a zoom, again, on the leading order and the next to leading order. I think I'm basically, yes, perfect, at the end of the time that I've been allocated. So, what I provided here is the description on how the density of state methods supplemented with a Robinson-Monroe step works for real action systems. It provides a control procedure to extract density of states, and it is very efficient at first order metastable systems, and they can be used to determine partition functions and free energies. For all of them, I provided an application. We need some improvement to solve the same problem, and here let me spend 30 seconds to remark that the same problem can be, in this approach, can be divided in two parts. One part is the determination of the row, the other part is the integral. So the determination of the row we have sorted. Now the part to solve, which somewhat you can say it's outside the core of the method itself, is how to do the integral with information. And then as potential or possible future applications, first of all, it's very interesting to keep testing the properties of the algorithm in scaling with the volume. Then it's very, very important to see how we can put the data that we have for the density of states in order to perform the integrals. I've given, probably I provided the first step in the direction of adding dynamical fermions. And finally, it would be nice to have with this method a proof of concept solution of the same problem. For instance, a small lattice in QCD. Okay. Thank you very much for your attention.
We have time for one or two questions.
At some point you mentioned singularities and that you avoid them by making an expansion. Is that correct?
Well, we have a 10. Yeah. So if you do, so say that you have, so this is your linear approximation of the density of states. Say. Now you want to Fourier transform. Okay? No problem inside the single interval, but this is a cusp. And you know that a cusp gives a contribution. So while this is good for some application, it's not good for other applications. So the idea is that if you have various points, then you can use the information coming from all of them, so that the density of states is a continuous function with no singularities, and then you can do the integral.
So the singularities are singularities.
The singularities are due to my approximation. The singularities I introduce. This is not the singularity of the function. Mm-hmm. So now the question is how to remove them.
Mm-hmm. Okay.
question?
Following up to our previous question, so this smooth version of the constraint, does it work everywhere that you showed? Because you introduced, as I understand, on the course of your studies. So would it solve all the previous problems before you introduced that? And can you, for example, combine it with a replica exchange?
Say again. So you say which method? Which method?
So when you placed the theta functions with a smooth Gaussian, so can you solve all the previous problems before you invented the smooth cutoff?
Yes, you can. You can also with discrete systems. I mean, you can discretize the Gaussian. You can do that. Yes, it's work in progress. So we are introducing techniques and testing them as we go along. I mean, there was no need there to introduce that technique, so it didn't actually. Well, in principle, for that system, we would have got away without doing it, but we wanted to take the opportunity to test something else.
Okay, maybe we should move ahead so we get back in schedule. So let's thank the speaker again. The next speaker is Philippe de Fortin.
I manage. Yep. Okay.
Don't put it in the context, try to hang it out. There will be no problem with the heading.